Recall that we've been solving equations, and last week we left off with this cliffhanger of an equation. We have a mixture of sines and cosines. Before, we had 2 cosine squared of 3x plus cosine of 3x minus 1 equals 0. And I traded that cosine for a sine. So we can't just inverse operations in reverse order our way out of this one. Also, we can't just substitute our way into a quadratic like we did last time, where we just said, let w be cosine of 3x, and then we get a quadratic. So we can't just substitute our way into a polynomial equation like we did last time. Or can we? What we're going to do is use a trig identity on the sine squared to make it match the cosine squared. What we know is that, I don't want to use red, sine squared plus cosine squared is equal to 1. So note, we have a Pythagorean identity that says cosine squared theta plus sine squared theta is equal to 1. Now, what we can use this identity for is to replace our sine squared with a cosine squared. Not just directly, they're not equal, otherwise we wouldn't have 2 separate functions. So we can use this to rewrite sine squared theta as 1 minus cosine squared theta. And then we will be able to make the substitution w equals cosine of 3x, which is what we were doing last week. So I'm going to replace my sine squared of 3x with 1 minus cosine squared of 3x. And now we will be able to make the substitution w equals cosine of 3x. Now, this worked out because the arguments of both the sine squared and the cosine were 3x. So we're going to be able to once we solve, so we'll be able to make the substitution, solve for w, replace that with cosine of 3x, and then inverse operations in reverse order our way out of the problem. If we had a sine squared of 5x and a cosine of 3x, we wouldn't be able to do that because I'd have a mixture of cosine squared of 5x and cosine of 3x, and I wouldn't have a substitution for that. I would have to do something else. But in this case, I'm going to use the distributive property and come up with 2 minus 2 cosine squared of 3x plus a cosine of 3x minus 1 equals 0. And so I'm going to have minus 2 cosine squared 3x plus cosine of 3x. And then 2 minus 1 is plus 1 equals 0. I'm not really a fan of leading coefficients being negative. This is our first class after algebra, so let's not mess with leading negatives. I mean, it's fine, but. So let's go through and change all the signs. Let's multiply everything by -1. And now we can make the substitution w equals cosine of 3x. So I'm not going to use orange. So my equation becomes 2w squared minus w minus 1 equals 0. We deal with the quadratic the same way we dealt with the quadratic last time. This problem is incredibly contrived to work out, so it happens to be factorable. We can have a 2w times a w. The only way to get 1 is with 1s. And I'm going to have a minus 2w plus 1w to get the minus w in the middle. So w is minus 1/2 and W is 1. So the equations that we need to solve are cosine of 3x is equal to minus 1/2, and cosine of 3x is equal to 1. Now we've just got a couple of trigonometric equations to solve. We go for a reference angle. So the cosine inverse of 1/2 is going to be 60 degrees. So our reference angle for 3x is going to be pi over 3, because cosine of 60 is 1/2. And we're going to have to put it in the quadrants where cosine is negative. Cosine is negative when x is negative, so that's in the second and third quadrants. So that'll give us two solutions for 3x. Pi over 3 in the second quadrant is going to be 120 degrees, or 2 pi over 3. We want to make sure that we get all the solutions, so I'm going to add 2 pi times some integer. That's what's going on in quadrant 2. Then I need to write our solutions for 3x in quadrant 3. So pi over 3 in the third quadrant will be 4 pi over 3. And then we'll add integer multiples of the period. Now we just need to divide through by 3. So we'll have 2 pi over 9 plus 2 pi over 3 times n. Also 4 pi over 9 plus 2 pi over 3 times n. That's for the cosine of 3x equals negative 1/2. We're also going to have to solve cosine of 3x is equal to 1. So if cosine of 3x is equal to 1, if we think about our unit circle, we're only going to get that at this point, the point 1, 0. So 3x is going to be 0 plus full circles. So 3x. But then we have to add integer multiples of the period. So plus 2 pi times n. Then we'll have to go through and divide everything by 3. 0 divided by 3 is 0. So we'll just get the 2 pi over 3 times n. So here are our infinite number of solutions. Any questions?
Why did you wait a couple extra steps before doing the substitution? Would something go wrong if you had done it right away?
Oh no, we could have done it right away.
Okay.
I wanted the quadratic to be, I wanted to see the quadratic in cosine and then do the substitution. I could have saved myself a lot of writing by doing the substitution right away. It would have looked like 2 times 1 minus w, I spelled 1 wrong. 2 times 1 minus w squared plus w minus 1 equals 0. And then we would have done the same things. Multiply by 2, combine the like terms, and I would still multiply by -1. 2 minus 2w squared plus w minus 1 equals 0. Minus 2w squared plus w plus 1 equals 0. So we could have done the substitution right away.
Got it. Thanks.
Any other questions? Rad. So this brings up an important point, or an important thing. Right at the beginning, I use this identity, this cosine squared plus sine squared is equal to 1. This is called an identity. An identity is just a kind of equation, and it's an equation that's just always true whenever whenever the expressions are defined. Since we know that where the trig functions come from, sine of theta is opposite over hypotenuse, cosine of theta is adjacent over hypotenuse, tangent of theta is opposite over adjacent. And in that right triangle model, opposite squared plus adjacent squared equals hypotenuse squared. All the trig functions are related in a huge variety of ways. So there's a lot of trig identities expressing relationships between our trig functions, or among our trig functions. Trig identities express relationships between trig functions. Trig identities express relationships between trig functions. An identity is just a type of equation. It's an equation that is always true. So this is just an identity is an equation that is true whenever the expressions are defined. An identity is an equation that is always true. When we solve equations, we are usually given conditional equations. That means there are certain conditions under which the equation is true, and there are certain equations that are never true, and those are called contradictions. So an identity is just one of those kinds of equations. So there's equations, identities, which are always true, conditional, sometimes true, and a contradiction is a type of equation, and that is never true. These are all just types of equations. So an example of a contradiction would be, oh, I used red for identities, so I'll use blue for contradictions. x plus 5 is equal to x plus 7. There is no number that fits this description. An equation that is a conditional equation, like the one that we just saw, x squared minus 2x. No, that wasn't what we saw. Either way, minus 3 equals 0. This equation is sometimes true. It's true for 3 and -1, but not true for any other values of x. So this has no solutions. This equation, x squared minus 2x minus 3 equals 0, is true as long as x is equal to 3 or -1. And then we have identities. These are equations that are always true. And I like using this x plus x equals 2x because we always replace 2x or x plus x when we see it with 2x. That's called simplifying. That's because x plus x is always equal to 2x. So trig identities just express relationships between the trig functions. Our job as trig students is to just remember all the trig identities. All of them, all the time, in perfect detail. That's actually not true. What's more important is to remember that there are trig identities. So if you're doing some problem and you get stuck, there might be some trig identity that will help you get out of it. So remembering that there are things like double angle identities and half angle identities and sum and difference identities is much more important than actually remembering all those identities, because you can always look them up if you need to. There are certain ones that you just have to be carrying around. It's totally okay if I ask you what 917 times 342.8 is equal to, and for you not to instantly know what the answer is. That's perfectly acceptable. You're going to have to write something down. You're going to have to think about some calculations. You're going to have to grab a calculator. But it is completely unacceptable at this point in your mathematical career to be asked what 7 times 8 is and not know that it's 50, whatever it is, 50 something. That's not okay. At the beginning of this semester, it was perfectly okay for me to say, what's the sine of 30? And you have to stop and think and imagine that 30-degree angle in the 30-60 right triangle before you come up with a half. At this point in your mathematical career, it is not okay for me to say, what's the sine of 30? And for you to not instantly know that it's a half. You just got to know some things, like right away. You don't get to look that up. You know what I mean? It'd be like, imagine if you got into your car or you got into a car with someone and they said, all right, hang on. And then he pulled a little card out of his wallet and said, all right, step 1, fasten seatbelt. Oh, okay, click. Step 2, depress clutch. Oh, yeah. If you got in that car and someone pulled out a card with notes on what to do, you're getting out of that car. It's not acceptable to not know that stuff. You know what I mean? Yeah, you could look it up, but you shouldn't have to at this point. Trig identities, it just becomes kind of fuzzy of where the line should be drawn. There are some that you have to remember and some that you just have to remember exist. And then some that you can kind of forget exist because you'll have other ones to back them up. So let's talk about the different kinds of identities. And I'm going to organize them similarly to the book. I'm going to use the book's organization. So the book described three kinds of basic trigonometric identities. These are reciprocal, quotient, and Pythagorean. Reciprocal, quotient, and Pythagorean. These are definitely ones that you should be carrying around with you. All right, so here they are. The reciprocal identities are the relationships between sine and cosecant, cosine and secant, and tangent and cotangent. So reciprocal identities are the ones that say sine of theta is the reciprocal of cosecant theta. Also, cosine of theta is 1 over the secant of theta. This is usually just how we define secant and cosecant as the reciprocals of cosine and sine. And tangent of theta is 1 over cotangent theta. This is usually how we introduce secant, cosecant, and cotangent. So those are the trig functions called secant, cosecant, and cotangent. Of all the trig functions that used to be running around, these are the six that we work with the most: sine, cosine, tangent, secant, cosecant, cotangent. And at that point, we're like, oh, you know what? We have calculators now, so we're good. Your quotient identities involve tangent and sine and cosine. So tangent is sine theta over cosine theta. We can combine this with the reciprocal identity and come up with that cotangent of theta is cosine theta over sine theta. And then you have your Pythagorean identities that come from the opposite squared plus adjacent squared equals hypotenuse squared. So the Pythagorean identities say that sine squared theta plus cosine squared theta is equal to 1. They're all going to be based off of this one. This is the one to know. You could remember, if you like alphabetical order, you can also go cosine squared plus sine squared is equal to 1. I try to alternate between the two orders, but it doesn't really matter. All the rest of them, we're going to use reciprocal identities and quotient identities to get different Pythagorean identities. We're also just going to use some subtraction to get other Pythagorean identities. So sine squared plus cosine squared is equal to 1. I can solve this like we did before for sine squared and get two more versions of this. So sine squared theta is 1 minus cosine squared theta. And I could do the same thing with cosine and say that cosine squared theta is 1 minus sine squared theta. We could also take this basic Pythagorean identity and combine it with a quotient identity. If I take this Pythagorean identity and divide everything by cosine squared theta, I can write sine squared over cosine is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. So combine the Pythagorean identity, the quotient identity, and the reciprocal identity into this variation of the Pythagorean identity. And there are two other versions of this as well. So here we have the equation, the identity solved for secant squared. I can solve it for tangent squared by saying tangent squared theta is equal to secant squared theta minus 1. Or I could solve it for 1, and I could say that secant squared theta minus tangent squared theta is equal to 1. Now that was taking our basic Pythagorean identity, sine squared plus cosine squared equals 1, and dividing everything by cosine squared. This raises the question, what if we went through and divided everything by sine squared? Will we get another one? And the answer is yes, we will. And no one was surprised by that. So I'm going to take my sine squared plus cosine squared equals 1 and divide everything by sine squared this time. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared. 1 divided by sine squared is cosecant squared. And once again, we have two other versions of this just by subtraction. Here's the equation, the identity solved for cosecant. We can solve the identity for cotangent and say that cotangent squared theta is cosecant squared theta minus 1. And we can also solve it for 1 by saying that cosecant squared theta minus cotangent squared theta is equal to 1. All of these 9 Pythagorean identities are derived from sine squared plus cosine squared equals 1. That's the one to know. The rest you can just kind of develop on the fly. Although it's handy to remember tangent squared plus 1 equals secant squared. And it's fine to completely forget about 1 plus cotangent squared equals cosecant squared. For reasons. So here are a bunch of identities that we need to remember. The primary one to remember in the Pythagorean identities is the sine squared plus cosine squared equals 1. This is the one to know. That's the one. Any questions? I just realized I left some off. It was important that that get recorded for the YouTube. That would be the one to know. All the rest you can derive from that one. If you want to be different, say, I always use tangent squared theta plus 1 equals secant squared theta, and I derive everything from that. That's if you want to be weird. But know that if you're trying to be weird by doing that, you're really trying to be weird. So you're not actually weird. You're just trying to be weird. So find somewhere else to be different, I guess is what I'm saying. You know what I mean? All right. So what do we do with these identities? Well, we saw in the previous equation, we can get something that we want. But that was a super contrived example. But they're all going to be super contrived example. What do we really do with these identities? The main thing we do with these identities at this point in your mathematical career is reinforce your algebra skills. No lie, that's the big thing that we get out of this. It reinforces your algebra skills and it improves the way that you read mathematical equations and mathematical expressions and equations. It helps you read better. It's good exercise for that. It's not like you're going to be working on sending rockets to Mars with humans inside them and have to remember that tangent squared plus 1 equals secant squared. No one's going to write that scene in a movie. It's like, oh, what will we do? And Jeff Goldblum was like, hang on, virus. What if we just use tangent squared plus 1 equals secant squared? If that sounded dumb, that's how dumb that stupid virus scene was. Thank you, Independence Day. I don't mean to hack on Independence Day. I mean, it's perfectly acceptable as a movie. It's fine. It's fine. It's fun enough to overcome any awfulness in its execution. So. I mean, who wouldn't greenlight the movie? It's like, well, hey, let's have Will Smith fight some aliens. And then somebody's like, I don't know. That sounds like a great idea. That's going to take a lot of money. Oh, you're going to get a lot of money to do it. It's like, okay, let's do that. Who else can we get? Then at the end, they're like, oh man, maybe we should have spent some money on a writer. And they're like, oh, nah, I'm just kidding, writer of Independence Day. So one of the activities that we might be called upon to do is to simplify an expression or verify a trigonometric identity. So let's suppose that we have an expression. I'm just going to steal this one because it's pretty cool. Let's suppose we have an expression that works out to tangent x times sine of x plus cosine x. Oops, there it is. So whatever we were doing, we came up with this expression. I'm like, oh man, I wonder if there's a better way to write this expression. And you kind of know that there must be, because otherwise I wouldn't have said it. I was saying, oh, this is perfectly acceptable. Leave it alone. But it's a bunch of trig identities, and they're all related. I got this tangent and the sine, and I know tangent is related to sine and cosine. So I'm going to replace tangent with sine over cosine. And so this first expression is going to look like sine squared over cosine plus cosine. And now we get into the algebra test part. What we notice is that we have a fraction. That first term is a fraction, and the second term is a fraction with a different denominator. So I'm going to read cosine as cosine over 1, and I'm going to add fractions. Let's see what that gives us. So the denominator of this first fraction is cosine, and the denominator of this second fraction is just 1. But if I multiply by 1, great trick of mathematics, now I have a common denominator. And so now my expression looks like sine squared x over cosine x plus cosine squared x over cosine x. Now we have a common denominator and we can add those together. We only add things that are the same, and when we add them, it doesn't change what they are. And in the case of fractions, sameness is a common denominator. So now we have a common denominator. And now we're looking at sine squared plus cosine squared, which was the whole thing that was supposed to happen in this expression. Sine squared plus cosine squared we know is equal to 1. Because Pythagorean identity. And now we have this expression 1 over cosine. I can replace that with secant using a reciprocal identity. So instead of having tangent x sine x plus cosine x, we can replace that all with secant x. We now have a new identity, which is really kind of a niche identity. But we know that now tangent x sine x plus cosine x is equal to secant x. The only reason I didn't list this in my basic identities is that it doesn't happen often enough for us to single this one out and say, this is one we really need to remember. Like this sine squared plus cosine squared equals 1, that happens all the time. And it's going to be really important to remember that. Tangent is sine over cosine, that happens all the time. Even in these non-contrived problems, just when we're going about our daily mathematical lives. This is a little bit niche. If you're a dungeon master and you put this as one of the puzzles in your dungeon, no one's going to remember it. But if you put like sine squared plus cosine squared to make sure people remember 1, they will remember that. I know you're thinking, who's going to put math puzzles in a dungeon for D&D? Well, a math professor probably would. So what's your job going to be? Your job is going to be making sure that you remember all of these identities. You want to make sure you start remembering them quickly because more will show up. So if you take a look at just the table of contents for chapter 5, tells you how many identities you're going to have to be dealing with. First section is just called Trigonometric Identities. Like, oh, it looks like we're going to have this whole chapter in one section, but then more appear. So sum and difference identities, double angle identities, half angle identities, product to sum, and sum to product identities. So there are many, many more. You don't have to memorize them all. The bigger thing, the more important thing, is to know that such identities exist, so that when an opportunity arises to use one of them, you say, I think there's an identity for this. I don't like this cosine squared. I would rather have a cosine of 2 theta. I wonder if there's an identity for that. And the answer is yes, there is. Now, you don't have to sit down and memorize all of these identities. It's better just to remember the identities. If that means that you, in your study strategies, if that means that you personally are going to have to sit down and memorize them, then so be it. It's better to just remember them rather than memorize them. All right. Start learning these basic identities. There's only 9. There's only 14 of them. That's hardly anything. And they're all related. Don't forget, a lot of these we defined with opposite, adjacent, and hypotenuse. And that sine of theta was opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. Also, remember that opposite squared plus adjacent squared is hypotenuse squared. Here's where we get our Pythagorean identities from. Tangent is sine over cosine. If I take opposite over hypotenuse and divide that by adjacent over hypotenuse, the over hypotenuse part cancels out, and I'm left with opposite over adjacent. So it seems like a lot to remember, but that's only because it's a lot to remember. You have to remember all of it all the time in perfect detail. The big advantage that you have is that it's all related. All these 14 identities are all related to the first thing that we did in this class, which was define our trig functions, sine, cosine, and tangent, in terms of opposite, adjacent, and hypotenuse. All right, now that's going to do it for today. Everybody have a good couple of days. I'll see you all on Thursday. Have a good couple of days, and thanks for playing.